All right, Algebra 2, check it out. I'm going to go through Unit 11, test review number 1, hit some specific questions on here, kind of talk through and work it out, and hopefully clarify anything as you prepare to take the test on this. So, starting with number 1, we are going to use the special right triangles to solve for x and y. Our special right triangles is all about a relationship between the sides. The side across from our 30-degree angle, the relationship, and we've used different letters throughout. I'm going to stick with u. So we're going to call that just u. Across from our 90-degree is 2u, or u times 2. And across from our 60-degree is u rad 3. So what we'll do from here is we're going to look at the information we have and we're going to say, okay, with this piece, is there enough here to solve? And there's not. Down here, is there enough here to solve? And there's not. Right here, we have information. This was 6 rad 3. It was cut off in the, I wanted to say printing, but this isn't printed. So it was cut off in the making of a PDF. And it corresponds with u rad 3. So if we were to take that information, we can set it equal to each other. So u rad 3 is equal to 6 rad 3. And what we're doing from here is we are working to get u by itself. Right now it's multiplying with rad 3. So we are going to divide rad 3 from both sides. Those cancel. And u equals 6. We can now use that information to apply it to our other two sides. If u equals 6, then right here, 2u is really 2 times 6, which is 12. So our x side is 12. And then if u equals 6, then I can replace that u here. So 6 equals y. And so y equals 6, nothing to solve for there. I'm just going to jump down, and we have 12 and 6. Even though I wrote y for whatever reason. I did want to put a disclaimer at the beginning of this video. There are a lot of moving parts here. It's one thing to solve them out without having to multitask and speak out loud through the process of what's going on. It's another thing to try and speak through the process while solving these. So please be patient with me if I make mistakes or if you catch mistakes. I promise I know how to do it better than my mistake suggests. A lot of times it's because I'm processing several things at once as I'm trying to verbalize what's happening in a way that makes sense. So number 2, we're working with a 45, 45, 90. And the relationship here is that each of these sides, each of the legs, are the length u, and our hypotenuse is the length u rad 2. So we're going to look at our information. Can't do anything with that. Can't do anything with that. I have enough information to work with here, so I'm going to set that equal to 0. I have u square root 2 equals, sorry, not equal to 0, equals to 9. So we're saying them equal to each other. And now I am solving for u. I need to get u by itself, which means I'm dividing rad 2 to both sides. Those cancel out. Unlike number 1, where they canceled out on both sides, we're left with u equals 9 divided by a radical 2. Now the problem with this is that we do not leave radicals in the denominator. So we are going to rationalize the denominator. It's a huge part of this unit, and if you struggle with it, follow along because you need to know how to do this. It's really critical to the mechanics of what we're doing from here forward. So in order to get rid of the denominator that's radical, we are going to multiply the fraction by the value, by the radical value in the denominator. So if I multiply rad 2 to both sides. Now what happens here, I'm going to write it out right now. I'm going to shortcut later on. This becomes square root 4, and the square root of 4 is 2. So if you notice, Essentially what happens here is that when we multiply a rad2 by a rad2, it just becomes the regular version. It just becomes a regular 2. Unless you really need to write that step, we should be at the level now where we can kind of skip through it. So my answer is going to have 2 in the bottom, and then 9 times rad2 on top stays as 9 rad2. The last thing we would do is check to make sure that we don't have anything that reduces. 9 over 2 does not reduce. We cannot reduce these 2's because one is inside the radical and one is not. So they are not like numbers. They're not the same number to reduce in the first place. So here's what we have. Taking this answer here, u is equal to 9 square root 2 over 2. I'm now going to apply that to each of my legs. If you notice, both of my legs have the same value of u. So if I were to replace u with 9 square root over 2, square root 2 over 2 equals x. If I were to replace here y equals 9 square root 2 over 2, and we've found the value for both x and y. They are the same. 9 rad 2 over 2. 9 rad 2 over 2. All right. Jumping down to number 3. Again, we are working with relationships. So the relationship here on a 30, 60, 90, we're going to map out across from our 30-degree angle. Now, I know this does not look like a 30-degree angle, but we are not going on how this looks. We are going on the information that we have. So across from our 30-degree angle is u. Across from our 90-degree angle is 2u. And across from our 60-degree angle is u rad 3. Now we're going to take a look at the information we have. Can't do anything with either of those, but I do have enough information here to set up a problem and solve. So I have u rad 3 set equal to 10, that length of the side. I need to get u by itself, so I'm dividing rad 3 to both sides. Oop. I don't know what happened there. And I'm falling apart. Rad 3. These cancel. Again, we're going to rationalize the denominator. I'm going to work through it a little bit quicker than I did the first time. 10 divided by rad 3. In order to get rid of rad 3, we multiply it to the top and the bottom. I do write that step. Now on top, I'm going to get 10 rad 3. On the bottom, I'm going to get a regular 3. I'm checking to make sure that 10 and 3 do not reduce. They do not. So that's my kind of formal answer there for u. U equals 10 rad 3 over 3. Perfect. We can apply that to both the other pieces. So if I were to replace u over here and say 10 rad 3 over 3 equals y. There's nothing to solve for or do. That is the value of y, 10 rad 3 over 3. Over here, x equals 2 times u, u being 10 rad 3 over 3. We can multiply 2 over 1 times 10 rad 3 over 3. My numerator multiplies with my numerator, so I'm doing 2 times 10 to get 20 rad 3. My denominator, 1 times 3, gives us 3. We check again. Can we reduce? 20 divided by 3, will those reduce? They do not. So my value for x is 20 rad 3 over 3. All right, and we're going to take a quick look at number 4. Again, it's all about identifying relationships in these. The relationship here is that we have u and u, and we have u rad 2. Now in this one, this is a 7 rad 2. It's cut off. We look for the one we have information about, which is this one. I'm going to solve. I'm going to use this workspace over here. U rad 2 equals 7 rad 2. I divide that rad 2 to both sides to get u by itself. These are going to cancel each other out. These are also going to cancel each other out, so u equals 7. So now I can say y equals 7, x equals 7. That's my value for u, 7 and 7. All right. If you see here, I've already built out my 6 trigonometric functions. I'm going to find the value for each. We have some information here. And the first thing that we're going to need to do is figure out this missing side. So if I have 9 is one of my legs, b is my other leg, and then c squared is my hypotenuse. So I'm saying 9 squared plus b squared equals 13 squared. 9 squared is 81 plus b squared equals 169. I'm going to subtract 81 from both sides to get b squared by itself so that I can square root both sides. 81. B squared equals 9 minus 1 is 8. That's going to give us 88. Great. Square root both sides. Square root of b squared is b. Now the square root of 88, I'm going to break this down to 2 times 44. And that's 2 times 22. And that's 2 times 11. And we are looking for groups of 2s. So there's a group of 2. One gets caught, one makes it out. So I'm going to zoom in here. B equals 2 on the outside. These both don't have like number partners. We use these up. They don't have like number partners, so they get multiplied back up on the inside. 2 square root 22. Okay, so b equals 2 square root 22. So that is the length of this side. Oh, you put it in red, I guess. 2 square root 22. Okay, now that we have that, we have our theta over in the corner here. So this is where we're going to orient ourselves. And we're going to look across from theta is our opposite side. Across from the 90 degree is our hypotenuse. That one's easy to label. And then next to our theta is our adjacent side. So we have adjacent, opposite, hypotenuse. So now we're going to be able to go through and figure these ratios out. Sine theta would be, sine is so, opposite over hypotenuse. So I'm saying 9 over 13. And then cosecant, which maps with sine, or kind of corresponds with sine, as the inverse. So we're going to say 13 over 9. Okay, cosine, we're using adjacent and hypotenuse. So the adjacent over the hypotenuse would be 2 rad 22 over 13. The adjacent over the hypotenuse. There's no radical in the denominator, so I don't have to rationalize anything. And then for secant theta, we take the reciprocal. So for this one, we're taking 13 over 2 rad 22. And now there's a problem because 2 rad 22, I can't have rad 22 in the bottom. So I have to rationalize. I'm going to multiply rad 22 to the top and the bottom. And these combine to just make a regular 22. So I have a 2 that was sitting out front, this 2, times the 22 that those combine to be, which will make 44. And then on the top here, 13 times rad 22 is 13 rad 22. So this is my, they don't reduce, 13, 44 are not going to reduce. So that's my secant theta. And then for tangent, tangent is opposite over adjacent. So we're taking our opposite 9 over our adjacent to rad 22. Boo, we have to flip this, or we have to rationalize it. We don't like rad 22 in the denominator. So again, I'm multiplying rad 22. Down here, my rad 22's the square root cancels out to just make it a regular 22 times 2, which is going to give me 44. And then up top I have 9 rad 22. And I'm checking these will not reduce, so I am done and found there. So I found that one. So there's all, oh, that's not all 6 of them. Here's what I'm going to do. I could take what I found, take the reciprocal and solve it out. But the original that I was working with, if I take the reciprocal of it, I end up with the same value. So 2 rad 22 over 9, and then I don't have to rationalize anything. Kind of nice. Okay. I'm going to run through 6 as quickly as I can. I told myself I wasn't going to do every problem, and now here I am doing every problem. So we've got to figure out this missing side first. So that's what we've got to find using the Pythagorean theorem. 9 squared plus b squared equals 15 squared. That's 81 plus b squared equals 225. I should know this, but let me just double check to make sure. Yeah. And then I'm subtracting 81 from both sides. Okay. And that means b squared equals 144, which is pretty nice. We have a Pythagorean triple here. B equals 12. The square root of 144 is 12. So there's my missing length. Now that we've done that, and we don't have any radicals that we're working with on our side length, so there's not going to be any rationalizing, which is nice. We're going to base ourselves on theta. From this corner, the opposite is 12, the adjacent is 9, and the hypotenuse is always across from the right angle of this one being 15. So now we're just using those relationships. Sine theta. Sine is O over H. So I'm saying 12 over 15. We can reduce that. 3 goes into both of them. 3 goes into 12 4 times, and 15 5 times. We can flip that over. 5 over 4. Cosine, we're taking our adjacent over our hypotenuse. So we're saying 9 over 15. Those will also reduce. 3 goes into 9 3 times. It goes into 15 5 times. Flip that over. We've got 5 over 3. And then tan theta, we are doing TOA, opposite over adjacent, so 12 over 9. That also reduces, 12 over 9. 3 goes into both of those, 4 over 3. And we take the reciprocal of that, 3 over 4. All right. That's some of the bulk of being able to use this stuff, figure these things out, especially rationalizing there. All right, let's talk about converting radians to degrees. I've already done this work. So when we are converting radians to degrees, if we're given the radians, then we are multiplying by 180 degrees over pi. And you see some things canceled out here. 3 and 180 cross-canceled to be 1 and 60. 3 goes into 3 once. 3 goes into 180 60 times. Pi and pi cross-cancel, and I'm left with 5 times 60 to get 300. Again, 180 over pi. So I cross-cancel. 5 and 180 cross-canceled to give me 36. Pi's canceled, and 7 times 36 is 252 degrees. And then finally, 180 degrees over pi. When I multiply that, 6 and 180 reduced to 1 and 30. 6 goes into 6 once, into 180 30 times. That degree sign is still there. It's not canceled. My pi's cancel out. And we do 25 times 30 to get 750. There is a negative. When I do a negative times a positive, we get a negative. Okay, let's talk about 10, 11, 12, and then we'll be on to 13, 14, 15. And a lot of the concepts that we've used up here then get applied when we draw things in and then apply the trig ratios to the triangles. So in order to find our 6 trigonomic functions. So we can use this inside of this to get like what we did in 11.5. Okay, so as I continue to zoom in, we are multiplying this by pi over 180 degrees. So when we're converting degrees to radians, we multiply by pi over 180. I did some cross-canceling here. I cross-canceled using, I don't know what I used. I used something, and then I used something smaller. So I must have used 30. So 30 went into 120 4 times. 30 went into 180 6 times. And then I realized, 4 over 6, that can be reduced further to 2 over 3. So as long as you're comfortable with reducing, you could, if you see they're both even, you could just chunk it down by 2s until you can't reduce any further. I saw between 120 and 180. I knew that 30 would work. So, and then I just went further. The degrees sign in these cancel, and I'm left multiplying my numerators of 2 times pi and 1 times 3. This one's color coordinated. Hopefully that's a little bit more helpful. Okay, for number 11, I reduced by 15. Look, I was nice to myself and wrote a note so that I wouldn't stumble in the video. I did a little guess and check and just kind of figured out, 15. No, not 15. 45. I think I used 45. See? Here I'm trying to help myself and I just sabotage myself. 180 divided by 45. How embarrassing. That should be a 4. I reduced by 45. I think I did try and use 15 and then it's like, wait, there's a larger number. So I reduced by 45. 180 divided by 45 gave me 4. 315 divided by 45 gave me 7. So those are my new values that I'm working with. My degrees sign canceled out. And now I'm working with 7 times pi to get 7 pi, 1 times 4 to get 4, and my negative times a positive is a negative. And I thought I had it together for that one, and I sure didn't. Okay, and our final one, 15. We're multiplying by pi over 180 degrees. Our degrees signs cancel out. 15 and 180 reduces to 1. 15 goes into 15 once. 15 goes into 180 12 times. And then we multiply straight across. 1 times pi is pi. 1 times 12 is 12. Okay, and then we're going to talk about moving these. When we're moving positive direction, we're moving counterclockwise. And I have some notes here. So from here, this is our 0 spot. It's also 360 degrees if we make it that far. So 90 degrees is here, 180 degrees from 0, 270 degrees from 0, and then all the way around is 360. That's why when we have a number larger than 360, we subtract that out so that we can find the remaining piece, because we just end up all the way in a circle back around 360. So it's easier to subtract that out and then find it from there. For 270 degrees, I'm counting 90, 180, 270, and it's on that line there. For number 14, I do want to take a moment to kind of explain this a little further for anyone who is struggling with it. Here's the deal with number 14. If you notice in blue, I have 0 or 12. This is cut into, this is just using my kind of thirds or whatever. Track with me here. Every time we move 30 degrees is essentially what's happening. 30 degrees, 30 degrees, 30 degrees, 30 degrees, 30 degrees, 30 degrees, 30 degrees. What happens in radians is we're moving once, twice, 3, 4 times, 5, 6, 7, 8, 9, 10, 11, 12. When we convert degrees to radians, like we were working with up here, this first move reduces to this. This second move, if we were to calculate, so 30 degrees times our radian to get the number, it goes here. 60 degrees times our radian comes here. 90 degrees times our radian comes here. Okay? And so that's where these are coming from. 1, 2, 3, 4. It's kind of difficult on the wheel because we're being shown the green part. So I want you to see that it's pretty sequential. It's almost like a clock. There's 12 and we're going 1, 2, 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock. Think about on a clock, 12 and 6 are on opposite sides. 7, 8, 9 o'clock, 10, 11, 12 o'clock. The problem is that because these are over 6, they can be reduced. So it's not as sequential because a lot of times we're seeing this. 1 pi over 6, pi over 3, pi over 2. Well, it's 3 pi over 6, but that reduces to pi over 2. 4 pi over 6, that reduces to 2 pi over r. So on the chart, what you're seeing is the green, which is the reduced piece, and it's hard to kind of figure out where it fits. Personally, for me, I'm doing a lot of converting, multiplying so that my fractions have a denominator of 6, because then my brain puts it together where it's supposed to be here out of 12. For me, it's a lot easier. So if I'm finding now 7 pi over 6, I can move 1, 2, 3, 4, 5, 6, 7, and in red, it's this piece right here. And I moved this way. I don't know why I put... So that's my piece there. All that extra stuff is just there for you to see kind of how it works. Hopefully that clarified it for you a little bit. And then finally, negative 240. I wrote my negatives. I know that in red here, this is positive 90. In red, this is positive 180. In red, this is positive 270. And in red, this is 360, right? Positive 360. In blue, though, that was me moving negative. So in blue, I move negative 90, negative 180, and then in between 180 and 270, we have negative 240. So that's how I got that answer there. So hopefully those red kind of help clarify what's going on there. All right, I hope this was helpful, and good luck on your test. And again, it feels like we didn't cover some of the unit 5 where we were taking something like this or something like this and then finding the angle. Think about the angles that are being created here between my red lines. Okay, this angle is 30 degrees. If I was coming here, this distance is 60 degrees. And so that's where you're using your 30, 60, 90 triangle. There also is, I guess, just another quick note. Hopefully this is helpful. I don't want to over-explain, but gosh, if it can help one person, I think it might be worth it. So that's in blue. Let me see if I can pick another color that's going to pop. Let's do orange. That's a complementary color, I do believe. So we've broken this down using twelfths, right? 1/12, 2/12, 3/12, 4/12, 5/12, 6, 7, 8, 9, 10, so on and so forth. We can also break it down in eighths. We can have 1/8, 2, 3, 4, 5, 6, 7, 8. And those end up being pi over... now I'm not remembering. I'm going to jump to my other notes real quick here. 5, wrong ones. Ah, here we go. So here we're using pi over 4. So this is 1 pi over 4. This is 2 pi over 4. Ooh. This is 3 pi over 4. So every time we move, we count. This is 4 pi over 4. 5 pi over 4. 6 pi over 4. Gosh, I keep doing that. Pi over 4. 7 pi over 4. 8 pi over 4. And we're using our over 4 over 2 because they reduce the same way my purple is reduced to my greens. 2 pi over 4 would reduce to 1 pi over 2, so just pi over 2. 3 pi over 4 is fine. 4 over 4 is just regular pi. 6 over 4 reduces to 3 over 2 pi, or 3 pi over 2. 7 over 4, and then of course 8 over 4 pi, or 8 pi over 4 reduces to 2 pi. So also this reduces to 2 pi. So I know it looks like a lot. Watch this over again and over again. Hold your notes and look at it. And I promise you, it's a lot more simple than it looks because we're just counting in orders. And for my orange lines, I'm moving in increments of 45. 45 degrees, 45 degrees, 45 degrees, 45 degrees, 45, 45, 45, 45. So from here to here, 45. Obviously, this whole thing's 90. So that's when you'll know to use 45, 45, 90 special right triangles when applying to your 6 trigonomic functions, finding triangles or creating triangles within that. Okay, hope that helps.